Neural networks. What are they and how do they work? Let's break it down. Imagine that you're teaching a computer to recognize patterns the way humans do. That's exactly what a neural network does. It starts simple. Data goes in and decisions come out, and in between is a system that learns what actually matters. But to make that work, every single part of the system has to be built carefully so information flows smoothly and meaningfully. So let's break it down. With a neural network, you'll always start with the shape of the data because that decides what the model is even looking at. For example, if you're feeding it 20 numeric features, then you'll have 20 input spots. But if you're giving it a 64 by 64 grayscale image, that's 4096 pixel values. You're not making choices about any of the learning yet, you're just defining the doorway that the data will walk through. Once you know what's going into the neural network model, you have to decide what a single unit inside of that network does with the information. Each of these singular units is called a neuron, and though this name is vague, you can think of a neuron as a tiny unit that contributes to the overall decision the model will be making. Inside every single neuron, there's a process of steps which are inherent to neural networks that will take place. Each neuron listens to its inputs in a really specific way. Firstly, imagine that each connection to the neuron has a little dial called a weight. At first, all of those dials are set randomly, so the model doesn't really know who to trust. But as it starts learning, it turns those dials up and down based on which inputs help the model make better decisions. A strong positive weight means the model will listen very closely to that input, but a negative one signals that the model should move the other way when that input goes up. Over time, the model learns which signals matter most, almost like learning who gives the best advice in a group. Then there's something called bias, and you can think of this like the neuron's personal threshold. It's just a little wiggle that shifts the total signal before the neuron actually reacts. And this can be really helpful when the inputs are small because it gives the neuron that extra push to decide when to fire. Now, the total signal, which is the weighted inputs plus the bias, goes through something called an activation function. This is what gives the neuron a bit of personality. Without it, the neuron would always respond in a straight, predictable line no matter what the input is. A real-world data often isn't straight. It curves, it clusters, and it twists. So the activation function bends that line that makes predictions. A few examples are ReLU, which turns off the negatives and passes positives through cleanly like a simple on or off switch. And Sigmoid, which squeezes everything between 0 and 1, so it's perfect for probabilities. As for which activation function the model actually uses, that's your design choice as the coder. For deep networks, ReLU is the go-to because it keeps the learning stable and fast. And for binary outputs, Sigmoid is usually the choice activation function. You pick the one that fits your problem, and the neuron just learns how to use it. Now, while that's all very complicated, one neuron on its own can't do much, but put them side by side, all looking at the same inputs, and you've built a layer. The number of neurons in a layer, which is called its width, controls how many patterns the network can look for at once. Think of each neuron as an individual pair of eyes. Some notice the edges, others might notice the brightness, and together they see more of the picture. Once you have a layer, you can stack another one on top, and that's where depth comes in. Each layer learns from what the previous one found, so the first one might see simple details like lines or correlations, but the next layer combines those into deeper patterns. Bigger layers mix patterns into concepts, like how your brain combines edges into shapes and shapes into objects. This is why deeper neural networks can find more complex relationships as long as they have enough data and are trained carefully. At the end of the stacks sits your output layer, which depends entirely on the task. If you're doing a yes or no prediction, you'll have one neuron that outputs a probability between 0 and 1, representing a probability. If you're classifying something into categories, you'll have one neuron per class, and the output will show how likely each option is. And if you're predicting real values like prices or temperatures, the output will stay linear so it can take in any value. Everything before this layer exists to give the output the cleanest summary of what matters. Once the output layer has spoken, the next character enters, which is the loss function. Think of it as a judge that uses the model's prediction and the true value to create one number that says how wrong the model was. Once the loss has been calculated, it's the model's job to figure out why it was wrong, and that's where backpropagation begins. Loss sends a signal backward through the network starting at the output layer. Remember those connections between the neurons where there's a little dial for the weight? Well, each connection asks itself, if I had been a little stronger or weaker, would the final mistake have been a little smaller? That gradient measures something called sensitivity. It's a number showing how much each weight or bias should change to reduce future error. Now, when the signal moves backward to the previous layer, each neuron doesn't just get the same amount of blame. Two factors decide how much feedback it receives. First, it's how sensitive the neuron's activation was at that moment. So if the activation curve was very steep, that means a small change would have made a very big difference, so it gets a bigger sensitivity score. Second is how strongly its output influenced the next layer. If outgoing weights had a really big impact, then that neuron shares more responsibility. Together, these two ideas, sensitivity and influence, control how the blame from the loss flows backward through the network. So this makes sure that each neuron is only adjusted in proportion to how much it actually mattered in predicting the final value. Finally, we repeat this cycle over and over and over until the neural network is the best that it can be. By the time you finish, you've built a living system of math that learns from experience. So if you learned something from this video, don't forget to save it for the next time you're working with neural networks and follow for more.